Okay, thank you, Jens, for your words, and I'm happy to speak to you. First of all, you may wonder why I talk about const and Constexpr. The reason is quite simple. With C++20, we have three additional words having const inside, so we have to know what each const means. Constexpr, Constinit, Consteval, const is used in constant expression. You know, there's a lot of Constness inside C++20. Have a look here. Const, Constcast, Constexpr, Consteval, Constinit, and finally is constant evaluated. So the first part of my talk is about, I want to explain you this different constnesses. In the second part, which is a little bit smaller, I talk about the differences regarding function execution and regarding variable initialization. Okay, let me start with the more theoretical part, and I will show you always, or not always, but almost always examples which you can use afterwards. Okay, const. This is boring, you know? It's a C++98 keyword. And the reason is quite simple. It prevents const objects from getting mutated. Okay. There's also some const correctness for it, which describes this from a more formal perspective. And const, I want to say it explicitly, is a quality attribute of your program. So constness is a virtue. Const objects must be initialized, of course we know it. Cannot be modified, of course. Cannot be victims of data races. This is a very, very, very important observations. Two requirements for data races are mutation and sharing. And when you are const, there is no mutation, therefore there cannot be any data race. And const objects can only invoke const member functions. Okay, this was easy. So this is exactly what is said. When you declare member function as const, you cannot change the state of the object inside, such as well. Okay, this is an error. But here's the first thing a lot of people don't know. We have two kinds of constness. Physical constness and logical constness. This is physical constness, kind of. The object is const and cannot be changed. Okay, we know it. But there's also logical constness. The object is const, but could be changed. This means declared members that can be changed in const members functions. Let me put it another way. When you declare a member as mutable, you can change it in const member functions, and we call this kind of behavior logical constness. Let me show you a classical example. Here's an example on Compiler Explorer. And always the same. When I invoke this crash switch clang, I don't know why. Let me go to GCC. If not, I will switch to a different compiler. It will not run. Anyway, we have enough time. Let me go to the what is this? Vanbox. I don't know. This morning it worked. Sometimes it didn't work. Here we are. The same program, but now we see the output. So what's the program doing? Let me make it a bit bigger. I have a main program having vector about gthread. Gthread is the improved thread in C++20. And each gthread should execute this lambda here, you see? This is the kind of lambda I usually don't use because it has more than one line, but in this case, I do it. So this lambda takes the counter by reference, increments it, displays it, and increments it once more. And because this is performed concurrently, this operation on counters such as inc and get should be protected. And exactly this is what's happening here. You see, get is protected and inc is protected. Protected by a lock guard, having a mutex inside. And here's the key observation. The mutex is mutable because it models logical constants, but not physical constants. You see, it cannot be changed from outside. It's kind of const. You sometimes set it, sometimes release it. Therefore, I declared it as mutable. So this is a classical example for it. Okay, let me go back to my slides. And I promise the next example will work on Compile Explorer. Okay. A few additional words about constants, which are not so exciting, but anyway. By default, pass pointers and references to const. You see, const. Okay, this is easy. What does it mean to pass something by const? I had a few days ago a discussion with a few colleagues. This means you don't pass ownership with pointer and references, you only borrow it. This is the semantic of a pointer or reference. Don't passing ownership, only borrowing something. Means it could become a null pointer inside because it's changed outside in a concurrent environment. Because it could happen, you are not an owner. And additionally, when you have a pointer, you have to be sure that it's not a null pointer, therefore you have to check it. And here's a small exception of this rule. When you pass it by non-const pointer or non-const reference, this means this is a so-called in-out parameter. This is a parameter which means it is changed inside. Okay. Now, the last classical kind of slide, and then we become more modern. Only to make my point. What does this mean? We can apply const in different places in the case of pointers. What does it mean? This means this is a C star points to a char that is const. The pointer cannot be modified, but the pointer can. Okay. When you put const here, this means C star is a constant pointer to char. And when you put const here and there, this means C star is a constant pointer to a char. Here, I should start here, sorry. C star is a constant pointer to char. This means neither the pointer nor the pointee can be modified. And honestly, this expression looked terrible. I used this simple rule, read it from right to left. Without this rule, I cannot read it. Maybe, I'm not sure. Anyway, okay, this was the boring part. But now it becomes a little bit more interesting. In particular, a quite interesting use case or example. Constcast allows it to remove or add const or volatile. Maybe a few of you don't know that you can also use the Constcast to add constness or volatileness. Okay. And here comes my key point. My boss in my previous company always said, it's no issue. You can remove the constness from a const declared object and modify it. All compiler will do that. And you know what? This is a lie. You will see it in a few minutes. Have a look. Modifying a const declared object by removing its constness is undefined behavior. You betray your compiler, to be sure. You promised this is const and then you removed it. It's not a good idea. And the compiler will probably, my compiler does it in a few seconds, will, how should I say it? Will not reflect this operation. Next rule, don't use Ccast, such as this one, because you don't know what's happening under the hood. It starts as a static cast. If this does not work, continues as a const cast, and at the end, you apply a reinterpret cast. But from the reading of this expression, you have no idea. And now let me show you this, how should I say it, exciting example. Let me make it a little bit bigger. No, I cannot do it this way. I have to do it this way. I hope this is big enough. Have a look here. This is not interesting. I'm only interested in the output. Here's what I have. Totally boring stuff. Now you can read it. Here's what I have. I have a non-constant int. Okay. I create a pointer to it. So far, not thrilling. Then I use this pointer to change the value from 10 to 12. And when I output it, you see 12, as I expected. And here comes the undefined behavior. Show it to your boss or to my boss, my previous boss. I have a constant int with the value 10. I create a constant pointer to it, you see. Now I cast away the constness and I change the value from 10 to 12. And you know what? The value is not 12, it's only 10. The compiler thought, nothing can change here. I will not do that, or what else. Anyway, you have undefined behavior. And with a newer compiler, you see such, how should I say it, disturbing behavior. Okay, let me show you the next example. What you should not do. Here are a few variations. Of course, you can do it. Here's what you should not do. I have a function taking an int, taking a constant. Now I have a constant. With a constant, I cannot invoke a function taking int pointer. Okay, this is obvious. I have to cast away the constness and then I can invoke it. A function taking const pointer can be invoked with a const int pointer and a non-const int pointer. This is boring, but it works. And here's the undefined behavior. I have a char initialized with a. I create a char pointer to it. And now I can cast it with a ccast to int. And this is undefined behavior to make it sure. Now to write an a on the int pointer. But in case of a static cast, which I use here, wait a second. In case of a static cast, it works. Yeah.
Could you please increase the font size?
Okay, sorry. This is always default with, please say to me how big it should be.
I think that's fine.
Enough?
Yes.
And, okay, then I remember 17.
Okay.
Thanks a lot for your remark, but Compile Explorer has here a bad default. Okay, let me continue. Now I come to, you see, 98, 11, 20, 20, 20. So I come to C++ 11. The next Constexpr we have, or Constexpr expression. Okay, Constexpr means it can be evaluated at compile time. I talk in particular only about a function. This gives the compiler deep insight. Why? Because the compiler exactly knows what's happening. And this is the most important part for me regarding Constexpr. The most important part for me regarding Constexpr is not performance, it's code quality. When you write a concurrent program and you initialize something with a Constexpr, you have to guarantee that this is initialized at compile time. This means there is no mutation at runtime. This means there cannot be any data race because nothing is changed. Such as here, my double. And there's a special rule which many people don't know. When you initialize a const with a Constexpr, you see here, 5 is a constant expression. This becomes implicitly a Constexpr. This you see is explicit, but this is implicit a Constexpr. Okay, as I mentioned it, both values, my double and my int, are initialized at compile time, therefore thread safe. And this is what I mentioned about this special rule. And once more, I can't emphasize it much enough. In concurrent program as constant as possible. When I have to analyze your concurrent program, and I do it quite often, you know what I do? I look at each variable and I make a mark to it if this variable is not shared or is constant. Because if one of these conditions is fulfilled, I know there cannot be any data race issue. But when your program only consists of shared state, which is mutable, you cannot reason about your current program. This is way, way, way too heavy for our limited minds. You know what I mean? Okay. Let me continue with Constexpr. This is a Constexpr function we have with C++14, and you see it looks quite convenient. The rule to remember when you can make a function Constexpr is quite simple. Each dependency must be resolvable at compile time, and then it can become Constexpr. So the rules in 14 are quite easy, but in 11 they're quite not ugly, but quite complicated. You can even have variables inside Constexpr function, but they must explicitly be initialized with a constant expression. The only thing you cannot do essentially is having static or thread local variables. And here comes the key observation. This function does not mean this function has to run or must run a compile time. It means this function has the potential to run a compile time. You can use this function at runtime when you invoke it with runtime values, so non-constant expressions. It has to run at compile time when you use it in a constant expression. And therefore, we sometimes don't know if the function runs at compile time or at runtime. In particular, when you use it in an expression which does not enforce that it should run at compile time. Therefore, you can only hope for your optimizer, essentially. Okay, here's I will come back to this point in a few minutes. Here's an additional observation. These functions are pure. What does pure mean? Pure, you know, maybe from Haskell, pure function language. You may also know it from template metaprogramming because it's a pure functional language embedded in the imperative language C++. Pure means such a function produces always the same result when given the same arguments. This means when you invoke it with 5 and 10, you always get back the same result, which is in this case 5. This, how should I say it? This property is called referential transparency. A pure function has no side effect. A pure function only works in itself. You cannot see something which happens inside, outside. A pure function don't change the state of the program. Okay. And what are the benefits? I'm a big fan of pure functions, or Constexpr to say it differently, or Consteval, to which I will come later. They are easy to test and to refactor. Have a look. You only have to invoke it once and then you know this function works. Do you ever try to test random or time? What is the expected value? I don't know. But with a pure function, it's quite easy. You can easily refactor this function. Why? Because no one outside will see what's happening inside. But when you have a global here inside, you cannot change it from 5 to 10. Someone may be annoyed afterwards. What is also a benefit of pure function? You can change the sequence of invocations of pure functions, so you can reorder them. Why? because a pure function returns today the same result such as tomorrow. So it doesn't matter when you invoke it. They can be automatically parallelized. Have a look. There is no shared state, therefore you can automatically execute this function on a separate thread. There is no data sharing, so therefore there is no reason to protect anything. And here's a trick which is heavily used in Python, but maybe not so known in C++. I say the Python terms, maybe you know them. In Python, we have a nice feature which is called a decorator. What does a decorator do? It adds additional function to existing function and renames it, gives it the old name. So it decorates function with additional functionality. And you know what this there's a decorator which is called memorization. What does this decorator do? It stores in a function such as this one, a dictionary. A dictionary is what we call an unordered map, and stores the old results of the function invocations. And when you want to have a new result, just the old values are returned. Only when you ask for a new result, the function is once more invoked, and you store the result. This is caching. And to apply this kind of caching, you need a pure function. You don't want to store a random invocation. This would be a terrible cubicle. Okay. A few additional remarks. You can also apply Constexpr to your user-defined data type. This means you can initialize my double at compile time when it has at least one Constexpr constructor, such as this one. This function can be hybrid. It can have Constexpr and non-Constexpr member functions. But when you declare a Constexpr object of this class, or initialize one to be more specific, you can only invoke the Constexpr member functions, of course. And once more, this is by definition thread safe. And now I have a small C++20 feature which may be mind-blowing for you. And this is the following one. C++20 supports Constexpr containers and Constexpr std string. Sorry, you have to be specific. Constexpr std vector and Constexpr std string. What does it mean? Vector and string allocate their members on the heap. This means the memory allocation must happen at compile time. There's a small restriction. It has to be a so-called transient allocation. So the allocation and deallocation has also to be done at compile time. This is, of course, a restriction, but this is a mind-blowing feature for me. Operator new running at compile time. But this is not the end of the story. The more than 100 algorithms, the classical ones of the standard template library, are all declared now Constexpr. Why can we do that? Quite easy. When you declare a function as Constexpr, this function has only the potential to run at compile time, but you can even use it at runtime. Now have a look at my example. I cannot run this example because this example requires a Windows compiler and I cannot execute. Oh, I forgot to mention something. I cannot execute Windows on Compiler Explorer. I can only generate assembler code. But you see, it works. Believe me, when you read my book, it works. Have a look what I do. I invoke max element. And what is max element? A Constexpr function. And I want to have the result at compile time. I enforce it, you know. I say Constexpr, do it at compile time or the program should not work. And now have a look. I create a small vector, 1, 2, 3, 4. I sort it at compile time. All is done at compile time. This is Constexpr. And finally, I return the last element, which is the biggest one, which is 4. This means this result is calculated at compile time. And here for you in a different way, I do it here with a lambda. You see, a lambda, a Constexpr lambda, the same stuff such as here. And here I display the result. Once more, I calculate the biggest value of a vector at compile time. This is for me a mind-blowing feature. And only to show it to you, because I mentioned a few times to make it more obvious, let me show you an arbitrary algorithm of the standard template library. Why should I do that? Let me go for search. And you see, here we are. Since 20, all of them are declared as Constexpr. This is the difference between before 20 and with 20. All of them. Honestly, I will not show you all of them. This would be too much for my presentation and too boring for you. So let me continue. And now I come to the additional C++ 20 feature, Consteval. Consteval is quite similar to Constexpr. Consteval generates an immediate function, but there's one big difference between Constexpr and Consteval. A Consteval function can only run at compile time, you know? We have usual function which can only run at runtime. We have Consteval function which only can run at compile time, and we have function Constexpr which can run at run or compile time. And Consteval only at compile time. Consteval cannot apply to a destructor, and it has the same requirements as a Constexpr function, meaning what you can do inside. Have a look. This is a Consteval function. And I can take the result at compile time. You see Constexpr, because this is fine. But when I invoke this function sqr with 100, which is not a constant expression, this would fail. So it can only be executed at compile time. Additionally, we have Constinit. Constinit is, from my perspective, of course, it's a 20 feature. Constinit is also kind of mind-blowing. You will see in a few seconds. Constinit guarantees that a variable with static storage duration is initialized at compile time. And this is what is mind-blowing for me. You initialize it at compile time, but it is still mutable. What are global what does static storage mean? You have a global, something outside of a function, or the objects declared with static or external. They have static storage duration, and therefore you can apply on them Constinit. And these objects are allocated at program start, and they are allocated at its end. Okay. And they solve a terrible feature we have in C++. Sorry, this is not a feature. This is a side effect of how should I say it? Of a strange initialization. I don't know how to express it differently. First of all, you see this sounds not so good. Static initialization order fiasco. What does it mean? When you have one static in one translation unit, which needs another static in another translation unit, and they depend on each other, one needs the other to be initialized or some way in this way. You don't have a guarantee which one is initialized first. We only have the guarantee that elements in one translation unit are initialized in the declaration order. declaration order, I assume. But we don't have the guarantee between translation units. A classical example, which many people love when they have it, is you have a singleton which depends from another singleton, and then therefore you don't know which one is initialized first. And therefore, with 50% probability, you will get the wrong or the right behavior. Why? Statics are initialized in 2 steps at compile time. They are 0 initialized if they are not constant. You see, at compile time, they are 0 initialized. And at runtime, they are dynamically initialized with the value you gave them. And therefore, we have a dependency here. Or in concurrency, I would say a race condition. And Constinit solves this issue. Have a look here. First, I want to show you this issue because this is really interesting. And this was really easy to show you this issue. I have a file, you see it here, .cpp. I have a square, and here I have a static A initialized. And you see this is outside of a function, therefore it's static or global. I initialized with the square of 5, which is 25. Okay, quite easy. And here I have the main program. It uses this static A from this other translation unit. And what it does, use it to initialize B. By the way, a translation unit is what you get when the after the preprocessor runs. This is called a translation unit, meaning after, for example, this header here is expanded. Okay, anyway. And here have a look. Now I compile both programs. I compile both CPP files, and then I link them in different order. You see, first main.o, then source.o, and then source.o, and then main.o. In this case, static B has the value 0. In this case, static B has the value 25. This does not mean this is the behavior expected. This is, of course, undefined behavior. You don't know it. But this is what I get with the GCC. And you see, this is not too promising. You should not do such stuff. When the link order, how should I say it, has an influence of the values of your statics. Therefore, what can you do? Just use Constinit. Have a look here. Constinit, and that's all. Constinit here, Constinit there. And now you can do it in both cases. This is Clang on Windows. In any case, you get 25. Okay, now I was maybe too fast. Let me go back. Now it's time for questions. Is it possible to declare a std string as const?
Yeah, I think this has been solved with a good border link.
I don't get you. Why should it not be possible to declare a std string as const?
Yeah, I think this has been solved with a Godboot link. We don't know like what the actual code is.
So now I have you, because this would really astonish me.
Yeah, that's there's a debate about the difference between Consteval and Constexpression and what problem Consteval solves.
No, the Consteval solves no problem, but you have the guarantee that this function can only run at compile time. With Constexpr, when you use, for example, let me show you something. So I want to show them because this makes my point clearer.
Function callable at runtime?
It's callable at runtime. Let me show you something which makes my point clearer. When you use this function here, Constexpr here,
yes,
inside std_out, you say std_out, and then you want to display the result of GCC of 5 and 10, maybe. And you know what? std_out does not enforce constant evaluation. Therefore, you don't have a guarantee if it's run as compile time or if it runs as runtime. I can only say to you by experience, Windows in this case most of the time runs at runtime, and GC done most of the time does it at compile time. And Consteval exactly solves this issue. When you declare this function as Consteval and you even use it in a non-constant expression, it's executed at compile time. I hope this was not abstract, too abstract, because I should have shown to you in a small compile explorer example. But this is the key difference. You have to guarantee only compile time. You can even use in a consteval function a Constexpr function. Once more, in a consteval function, a Constexpr function. And this means now the Constexpr function has to run at compile time. So for me, Constexpr is hybrid, you know, runtime or compile time. Sometimes it has to run at compile time. Sometimes it has to run at runtime. Sometimes we don't know. Okay. I will go, maybe this was not so good, this explanation. Oh, no, it was a very good explanation, but I want to say it from different perspective. I will come to these differences here, because these are exactly the differences why I made these examples. Was there a remark, Jens?
There's another question about why Constness is not default in C++ 20 like it is in Rust.
Sorry,
that's just not possible.
This would not work. You have to discuss with Bjarne, and Bjarne would say he would say something like, we cannot break all code.
Yes.
This is just a simple observation. Let me add a few remarks. We are not in Python. In Python, Guido was bold enough to make a breaking change from Python 2 to Python 3, but it took him only 10 years to make this transition from 2 to 3 perfect. 10 years. And the second observation I want to make,
Rust could not do the, like, let's get like C++ and be not constant by default. Rust couldn't do that either. So once you decided that that is your language rule and you have an existing large code base, it gets very hard to set the defaults correct again. And that's the general problem of C++, that a lot of our defaults are, in today's age, are more seen than we should have picked something else. But this
is exactly my second remark I want to make. Nico, you should too, said a very good sentence. Let me rephrase it. C++ is the programming language in which we make each time the wrong default. Something like that. Maybe the sentence was in German, I don't know it, but you know what it means. By default, variable should be const. But now it's too late. 40 years too late.
Yeah, that's
okay.
True.
You're totally right. Your observation is right. It should be constant, and once more, constant is a virtue. Make your programs as constant as possible. Let me jump to the differences part, and now I hope I make the differences clear between usual function, Constexpr function, Consteval, Constinit, and what this all means. Because you see, we have a lot of Constness now inside C++. Okay. First of all, I didn't mention it so far. Oh, sorry, I forgot my last point. Anyway, sorry. Is constant evaluated? Afterwards, I make the difference. Is constant evaluated? This is an example from CPU reference. It's really interesting. Have a look. This function is declared as Constexpr. This means this function could run at compile time, but also could run at runtime. And here's the code, you see? When it runs at compile time, you execute the if branch. When it runs at runtime, you execute the else branch and apply stud power. This is necessary because stud power is not Constexpr, which is a pity. You see, this is kind of crazy stuff you can do in C++ 20. You can write a function which does different things at compile time and runtime. different algorithm and maybe a different result, but I don't know. I don't know this expression too good to say it always returns the same, such as here. This is constant evaluated. This is for me mind-blowing because you have here a part which cannot run at compile time, and this is possible to be used in a Constexpr function, but only when you use it in this kind of logic. Okay, and now to the clearing part. Let me make the difference clearer about function execution and variable initialization. Function execution. Here I have three different functions, and you see a usual function, a Consteval function, and a Constexpr function. All functions do the same, map n to n times n, so quite boring. And now have a look. When I invoke the square runtime function with a constant expression, I cannot have the result at compile time. This is not possible with a classical function. But I can do it with a Consteval function or with a Constexpr function. And you see this function runtime, compile time, runtime, or compile time. Exactly the name stands for when it could run. And now let me do it the other way. When x is not constant, meaning each invocation here cannot run at compile time because one dependency x is not resolvable at compile time. This means this function execution here, consteval, throws an error. I could show it to you here, but I think this is not no added value here. So let me just explain it here. Once more, this cannot be executed because x is not a constant expression. Okay, this was the difference between these three kinds of functions. Now let me talk a little bit about variable initialization. Have a look. I have Constexpr and Constinit. And here I have a usual variable and I add one to it and make it const. And now let's see the difference. First of all, I have to explicitly say it. This is a static. Constexpr and Constinit are statics because they are defined outside of main. Because Constinit cannot be used inside, which you will see in a few seconds. Have a look. When I want to increase res, it's not possible because it's constant. Okay, this is easy. When I want to increase Constexpr, it's not possible because it's const, you see. Initialized at compile time and const. But here's the difference. Constinit is initialized at compile time, but not const. This is the special feature of Constinit. You have the guarantee that it's initialized at compile time, maybe to fix the static initialization order fiasco, but it can be changed. Honestly, when I look at it, you have to read it carefully because there's const inside. You have to read it not as const in it, but as const in it. So the only stuff which is guaranteed is the initialization at compile time, but it is not const. And here's some additional point. When I make this both guys locals, you see they have they are on the stack, they have their own scope. I can use here my Constexpr to initialize it. This is trivial, but I cannot use here const in it. Now the question may be, there's one hole in this feature hole in this area. How can you initialize something at compile time which is local but can still be changed? You see? This is not local, so you cannot use const in it. When you initialize it at compile time using Constexpr here, then you cannot change it. So the question is, how can you initialize something in local scope at compile time, but it is still mutable? And here's the trick. You declare a Consteval function, and you assign the value to a variable which is not constant. And now you can, this means this function or this initialization happens at compile time, but afterwards you can change it. This is the rabbit hole. Okay. I was a little bit, maybe I was not too fast, but anyway, I'm done with my stuff. Let me, in a few seconds, repeat what I said, and then I'm open for questions, and we see how it goes on. I talked about the different flavors of Constness in C++ from beginning with 98, ending with 20. Of course, we know const, it's a 98 feature. We have const correctness. You should make by default all const. You can cast away or add constness or volatileness to a variable. Constexpr is a C++ 11 keyword, and this allows you to declare a function as Constexpr, which has the potential, once more, the potential to run compile time. And but you cannot be sure if it runs at compile time or runs at runtime. To be sure, you have to make it Consteval, but this is now a C++ 20 feature. And the last const keyword here is Constinit. Constinit means you can initialize a static at compile time, but this static is still mutable. And isConst evaluated is a type trait, and this allows you to ask if the function is evaluated or runs at compile time or runtime. And depending on compile time or runtime, you can do different stuff inside the function. And at the end, I talked a little bit about these three kinds of functions we have. We have usual functions, they can only run at runtime. We have Consteval function in 20, they can only run at compile time. And we have Constexpr function, which could run at compile time or at runtime. It depends on the circumstances, meaning when you use a Constexpr in a constant expression, it has to run at compile time. When you use Constexpr with a non-Constexpr argument, you can only execute it at runtime. And then I talked about variable initialization and about this nice trick, which I'm happy to show once more. This allows you to initialize something at compile time, which is still mutable, and it's local. This is the key observation here. Okay. Thanks for listening. Are there any additional questions? Okay, I see that there is no additional question in the chat. Sorry, Jens, you wanted to say something?
Yes, just giving the chat a little bit of time. Yeah, so I don't, as far as I see, all questions have been answered. There's just a little bit of chatting in the time. Yeah, seems like everyone is happy, and then folks will be able to join you in the lounge.
Okay.
But there is okay, someone points out that it's unfortunate that for const eval and constant expression it's implicit const. Or is there a deeper reason for that? Do you have an opinion on that?
No, for me, I never thought about it. For me, it's kind of given first, and second, it looks for me natural. And I was only astonished by Constinit because there's const inside and it is not const. This, you see what something strange is happening.
Yeah.
What is now happening, Jens?
Slides again. You're seeing
I say what I wanted to say, but I cannot show it.
Okay.
This is the example with Constinit. You have a const inside, but it's not const. This is a little bit crazy for me, you see? Only from the naming perspective.
There's one question about if we can expect to see compile time debuggers in the future.
This would be a nice feature, but I don't know it. But I have another idea, but I don't know if this exactly works. There was long time ago a nice template debugger, which is also a compile time feature. And I don't know what they could achieve. And this was called, this was created in Hungary, in Budapest, CPP shell or something like that. Meta shell, something like that. Search for this. Template debugging. You can debug templates and go back in time. So a template instantiation crash and you can debug it. This is a crazy feature. This is some feature built on the LLVM runtime. But I don't know anything about compile time debugging regarding Constexpr. Honestly, when you ask for such feature, write people such as David Vanderwater in email. I think he's the right guy. He's also the guy who implemented this Constexpr executed at compile time. He was responsible, as far as I know, for the specification, maybe it's also for the implementation of this feature. So he's a really expert in this area.
Okay. Yeah,
I'm only a trainer, sorry.
Link to Template, which is obviously also a tool for this. There's some compile time tracers, etc., and tools available. Okay, I think we're going to end the stream, and then we're going to see you in the lounge in a minute.
Okay, wait a few seconds, and I will be there.
Okay.
Okay, see you.